Hey there, chemists. Welcome to our second day of organic chemistry. Today we're going to be expanding on yesterday's introductory lesson, and we're going to be continuing on the same notes sheet that we were using from yesterday. Now, as a refresher, yesterday we discussed what is organic chemistry, why do we study it, and we started with our most basic organic molecule, a hydrocarbon. We spent some time talking about how to go from formula to name. We talked about identifying the three different hydrocarbons, alkanes, alkenes, and alkynes. And today what we're going to be focusing on is going from not only the name to formula, but name to structure and being able to kind of draw that structure from that name. So just as a quick review, when we're naming hydrocarbons, we have two steps to name that hydrocarbon. Step one, we're going to identify the number of carbons. The number of carbons is going to give us the prefix of our name. So, for example, meth, eth, prop, but, pent, so on and so forth, based on our number of our carbons. And then we have our ending or our suffix, and it's either going to be ane, ene, or yne, based on whether it belongs to the alkane, alkene, or alkyne family. So you're going to be using reference table P today for your prefixes, reference table Q to help you with identifying the homologous series to which your molecule belongs. And let's go ahead and dig in. So what I'd like us to do is draw a molecule of pentane in the box below. So when we are taking a look here at going from a name to a formula, we still want to break that name down and identify what types of bonds we're seeing and how many carbons we're going to have. So pent, P-E-N-T, tells us that we are going to have 5 carbons. Let's go ahead and do this in a different color. This is going to indicate that we have 5 carbons, and the ane ending indicates that it's part of the alkane family. And why that's going to be important to us is we want to be able to identify the types of bonds that are present. Now, as a refresher, alkanes have all single bonds, alkenes have a double bond, and alkynes contain a triple bond. So because this is an alkane, we are working with all single bonds. Okay, so now let's go ahead and draw out our molecule. So the first thing that we need to do is draw our 5 carbons. So we have 5, so 1, 2, 3, 4, 5. And I like to attach them all with single bonds, regardless if they're alkenes or alkynes to start, because that way we know that we have our 5 and they're all attached. So all single bonds, but this works because it is part of the alkane family. I actually don't need to adjust anything. What I need to do next is add in the hydrogens to satisfy the octet rule. So as a review, carbon can bond a total of 4 times. And based on the number of bonds it already has, that's the number of hydrogens we need to add. So for our first carbon, notice that I have 1 bond already. And so that's going to indicate that I need to have a total of 3 hydrogens attached to that carbon. Okay. The second carbon has 2 bonds already, which means that it can only bond to 2 hydrogens in the molecule. Our third carbon has 2 bonds and therefore can attach to 2 hydrogens. Our fourth carbon, again, 2 bonds, therefore it attaches to 2 hydrogens. And our fifth carbon has only 1 bond, so again, it's going to have 3 hydrogens. Now this picture of what we just drew, the Lewis dot structure, is also known as the structural formula. And our structural formula can be defined as the drawing of what the molecule looks like. Okay? And so structural formulas can be very helpful, as we've discussed plenty of times in the year. They can tell us polarity of molecule. That way we know whether or not it's going to dissolve or not dissolve in water. It's going to give us information about maybe whether or not it has a stronger, a high or low boiling point. We can get a lot of information from our structural formula. What I want to go from there is our molecular formula. This is something that we've been practicing with already. So our molecular formula, we can go ahead and define that as our formula that tells us the total number of carbons and total number of hydrogens in our formula. So we can do this two ways. We can go through and actually count from our structural formula the number of carbons and hydrogens, or you can use the generic CnH2n formula that is provided from reference table Q. Because this is an alkane, we're going to use CnH2n plus 2. So we have C5H, double that is 10, plus 2 is 12, C5H12. And just to confirm that that is in fact true, you can count it against your structural formula. Now, the first new thing that we're really going to be looking at here is what's called a condensed formula. And a condensed formula helps us in a sense that it helps us remove the lines. It eases up on some of the time it takes to draw the structural formula, but it also informs us a little bit more about how it's bonded still. So the condensed formula removes bonds from the structural formula, but it tells us still a little bit more information. So what I want to do here is I want to walk us through how to get the condensed formula. And so what we're going to do here is the first thing that we're going to do is we're going to go ahead and count our first carbon in line from left to right. Okay. Now our first carbon is one carbon and it has 3 H's attached to it. So for our condensed formula, we're going to end up with CH3. Okay, our second carbon here has 2 hydrogens, and so for our condensed formula, the CH3 is followed by CH2. Okay, our third is again CH2, so again, we're going to follow this by another CH2. Okay, followed by our fourth carbon, which is again CH2, so CH2, and then followed lastly by our fifth carbon, which is again another CH3. Okay, so CH3. And what this does is it allows us to it tells us more information than our molecular formula, right? Our molecular formula tells us we have a total of 5 carbons, but we don't really know just from looking at that what the structure would be. Those 5 carbons can be bonded in different ways. But our condensed formula takes it and it tells us the order, and it gives us a little bit more information on how things are bonded together. And again, what I'll do to kind of show you this is in class tomorrow, we'll go through and I'll show you exactly how you can go from condensed formula to structure, which is, I think, where you'll really start to see how helpful the condensed formula can be. Now let's do one more practice problem and let's complete this process for hexene. Okay, if you want to, feel free to pause the video and try on your own. If you are not super comfortable yet, that's okay. Let's do this together. So hexene, let's break that down. Okay, again, hex is our prefix, and guess what it stands for? It stands for 6 carbons total. Again, if you're not sure where these are coming from, this is coming from table P. Okay, and from there we have ENE as our ending, which means it belongs to the alkene family. And the distinguishing feature about alkene family is that it has a double bond. All right, so now we're ready to go ahead and start drawing it out, drawing this out. So again, the first thing that I like to do is just draw it straight across with single bonds. We can add that double bond in later, but just to make sure that we have all of our carbons, I almost said all of our ducks in a row, but all of our carbons in a row, let's go ahead and draw that out. So we have 1, 2, 3, 4, 5, 6 carbons. Now we need to add a double bond in. And here's where things get tricky. And we'll talk a little bit about how we kind of fix this problem actually in our next lesson. We don't really know where that double bond goes. So you know what? They didn't distinguish in the name where it goes. So you can choose where it goes. So if you did pause the video and you're going over this with me and you chose somewhere else for the double bond to go, that's totally okay. But let's keep things, I don't know, simple and just put it right there directly in the middle. Okay, so now I've satisfied my hex and my ene, and I need to go through and just add my hydrogens in. So again, we need each carbon to have 4 bonds. So carbon 1 has 1, so it has 3 hydrogens that are attached. Carbon 2 has 2, so it has 2 hydrogens attached. Carbon 3 has 3 bonds already, so it is only going to have 1 hydrogen that attaches. Carbon 4 has, again, 3 bonds, so it's going to have 1 hydrogen that attaches. Okay, carbon 5, 2 bonds, so it has 2 hydrogens, and carbon 6 has 1 bond, so it has 3 hydrogens. Now, you might be asking to yourself, why did Miss Daly choose to put the hydrogens on opposite sides around that double bond? And the short answer, without getting too in depth, is that we want to keep areas of dense electrons kind of away from each other, and dense masses away from each other. And so typically when a molecule is in nature, it's going to form so that it keeps those hydrogens away from one another. But again, if you put them on the same side, it's not incorrect as well. So if you drew them both up or both down, it doesn't matter. All right. Now what we want to do is get the molecular formula. So again, you could count through, or you could say, well, it's an alkene, it follows CnH2n. So that must mean if I have 6 carbons, that I have to have exactly double the hydrogen for C6H12. And lastly, going through and doing our condensed formula. I'm not going to do it all colorful this time, but let's do it together. So my first carbon is CH3. My second carbon is CH2. My third carbon is CH. My fourth carbon is CH. My fifth carbon, CH2. And my sixth carbon, CH3. And what's interesting and why this is helpful to us is because we can see directly right off the bat that each of these carbons right here only bonds to 1 hydrogen. This is going to be the indicator as to where our double bond goes. And just by looking at that, we know that our double bond is going to fall between those 2 carbons. Okay? All right, everybody, that's it for today. Tomorrow in class, we're going to continue practicing naming, formulas, and drawing, and then we will learn something new tomorrow. Have a fantastic rest of your day, everyone.